So in this model of consumption, I'm going to derive the Euler equation under these important assumptions right here. The first assumption is that we're going to keep it very simple and only focus on two periods. Period t, the first period, and period t plus 1, the second period in the future. In each of these periods, our consumers are going to try and consume one good, denoted C. So in the first period, it's going to be denoted CT, second period, CT plus 1. And then in each of these periods, earnings are going to be taken as given for our consumers. So we're not going to derive a function that explains earnings. We're going to assume that earnings are given to our consumer in each period. So yt in the first period and yt plus 1 in the second period. And then last but not least, in the very first period, but not the future period, our individuals are going to be given assets, and we're going to denote these assets AT. So there's going to be no AT plus 1 because they're only given these assets in the first period and not the second period. So in our two-period model, this is what utility is going to look like. So remember now that consumers consume C in each period. So CT for the first period and CT plus 1 for the second period. So they get utility from consumption, and utility is going to be equal to utility of CT, so utility from consumption in the first period, plus beta times utility of CT plus 1, so utility in the future. And that's going to be our utility function over the two periods. The reason we have beta is because consumption in the future is going to be less valuable than consumption today. So as a result, we have to include this discount factor beta. And what beta measures is the consumer's degree of impatience. And beta is contained within the closed interval 0, 1. So the closer it gets to 1, the more patient we are. So let's say beta was 1, for example, which it never can be because it's in this closed interval. But theoretically, if it was 1, then UCT would be not discounted whatsoever. So our consumer wouldn't care about consumption being in the future compared to consumption today. So as B increases, it means our consumer is more patient. Whereas if beta is closer to 0, our consumer is more impatient, meaning he's less willing to wait to consume, and as a result, it is discounted by a lot more. So utility of consumption in the future is going to be less when we discount it. More specifically, beta equals 1 over 1 plus delta, where delta is between -1 and 1. So as a result, beta ends up looking like this. So that's what our utility function is going to look like. And as you've noticed, I'm not going to specify any specific utility function. We're just going to keep it general. Just say u of CT and u of CT plus 1. You can enter a specific utility function, but just for this analysis, I'm not going to at this point. Another important characteristic of our utility function is that it is strictly increasing and strictly concave and has diminishing marginal utility. So in order to understand this, let's just pick either period, period 1 or period 2. I'm going to look at the first period. What this means is that it's strictly increasing, and so the first derivative is going to be greater than 0 or positive. And because it's strictly concave, this means the second derivative is going to be negative. And to better understand this, we can draw it on a graph. So let's just have CT on the x-axis and u of CT on the y-axis. Not very straight, I know, but you know, when you're in an exam, for example, make sure you do draw this with a ruler. But our function is going to look something like this. So as CT increases, utility does increase. So it is increasing. That's why this is greater than 0. but it's increasing at a decreasing rate, hence why the second derivative is greater than 0. So we have a concave function, and this is what we mean by diminishing marginal utility. If you've done any basic microeconomics course, you'll understand that this concavity is, we describe that with another term called diminishing marginal utility, and that's what this basically means here, which is another important point of our utility function that we need to remember. So because our utility function possesses diminishing marginal utility with regards to consumption, this means that any marginal increase in consumption, so CT or CT plus 1, increases utility but at a decreasing rate. So due to that, we now know what the indifference curve between the two goods, CT and CT plus 1, is going to look like. So if we draw CT plus 1 on the y-axis, CT on the x-axis, the indifference curve between these two goods is going to look something like this. Now, where diminishing marginal utility comes into this is when we have more of a good, what diminishing marginal utility means is that we get less utility from that good when we have more of it. So these lines right here represent that in an indifference curve. So as we can see here, let me explain before you try and understand exactly what these lines mean. But as we can see here, at this point here, we have a lot of CT and not much of CT plus 1. So because we have a lot of CT, we're not getting much utility from it, because the more we get of a good, although we do get extra utility, it's at a decreasing rate as we get more and more of it. So as we can see here, we have a lot of CT, but not much of CT plus 1. It's down here. So at this point, we're willing to give up a lot of CT. So just moving from here to here, we're giving up a lot of CT just to gain a small amount of CT plus 1. That's because we don't have much of CT plus 1 and we have a lot of CT. So we're willing to give up a lot of CT just to gain a small amount of CT plus 1. As we can see, this arrow here is much larger than this arrow here. And that's because we don't have much CT plus 1, and so any increase in CT plus 1, when it's very low, is going to increase our utility by a lot more than any increase in CT, because we have a lot of CT. So our indifference curve, due to diminishing marginal utility, is going to look like this. So we're also going to want to derive the slope of this indifference curve. And we know from any basic microeconomics course that the slope of our indifference curve, when between good x and good y, is going to be minus the marginal utility of good x over the marginal utility of good y. In this case, good x is CT, good y is CT plus 1. And marginal utility of CT, just to be more specific, is going to be the derivative of our utility function. We're just going to call it u dot. This is just u of CT and CT plus 1. And we're going to take the derivative of this with regards to CT. And so we're going to have marginal utility of CT over the marginal utility of CT plus 1. That's going to be the slope of our indifference curve. So because we haven't specified any specific utility function, the slope of our indifference curve is just going to be equal to this. If you recall our utility function, CT was just u of CT, so the derivative of u of CT is just going to be that. And remember, CT plus 1 had a beta multiplied by it. So as a result, the marginal utility of CT plus 1 is just going to be beta u CT plus 1. So 1 there. So that's the slope of our indifference curve here. So now that we've looked at the utility function and the indifference curve, which summarizes the relationship between the utility of the two goods, it's now time to look at the budget constraint. So we know that consumers want to consume more. They want more C. They want more CT, and they want more CT plus 1 because they get utility from this. However, how much CT are they allowed to consume? How much does their budget allow them to consume? And as a result, we need to derive the budget constraint in order to understand that. So the budget constraint is going to change over the 2 periods. So in period 1, the budget constraint is going to be equal to this. CT plus ST, remember ST is savings, is equal to the assets that we're endowed with, that we're given in the first period, plus the income that we get in the first period. So the income we get in the first period, plus the assets that were given in the first period, this is all of our income in the first period. And this is equal to how much we consume and how much we save. So what we don't consume, we're saving. And so that's going to be equal to everything that we are given. So that's this plus this. In the second period, however, our budget constraint is going to change. We're no longer given any assets in the second period. And also, what we saved in the first period can earn interest over time. So CT plus 1, consumption in the second period, is going to be equal to the interest rate, so 1 plus R, multiplied by our savings. So what we saved in the first period is now earning interest over time, which is contributing to our consumption in the second period, plus our income in the second period. So everything we consume in the second period is equal to what we get as income, plus the return on what we saved in the first period. So these are our 2 budget constraints for period 1 and period 2. So now that we have the budget constraint for period 1 and period 2, we now want to combine these 2 periods and their constraints to derive our lifetime constraint. Because remember, our consumer is only alive for 2 periods, period 1 and period 2. So if we combine both periods, we have the lifetime constraint. So this is just an R, I'll make that a bit more clear, which represents the interest rate, as I just mentioned. So to combine these 2 constraints, we're just going to use simple algebra. So as we can see, we've got an ST here and an ST here. So from this point on, I'm just going to be doing just some basic algebra. There's no economics, there's no understanding that needs to be done, it's just mathematics. So this constraint we can rearrange to ST equals AT plus YT minus CT. And this constraint we can rearrange to ST equals CT plus 1 over 1 plus R minus YT plus 1 over 1 plus R. We're going to set these both equal to each other because they're both equal to ST. And then that's going to equal AT. Oof, that's an A. Plus YT minus CT equals CT plus 1 over 1 plus R minus YT plus 1 over 1 plus R. We can rearrange this. It's a bit unclear, apologies for that. We can rearrange this to CT plus 1 over 1 plus R equals AT plus YT plus YT plus 1 over 1 plus R. And now we're going to call this W, which we're going to call our lifetime wealth, because this is everything over the 2 periods that we're given in terms of earnings and assets. So this whole right-hand side of the equation with the YT plus 1 discounted by the interest rate, YT, so income in the first period, and the assets that were given in the first period, we're going to call them W. So that's lifetime wealth. So now consumption in the first period plus consumption in the second period divided by the interest rate equals W, which is our lifetime wealth, which is everything that we get, which is equal to everything equal to consumption over the 2 periods. So now we can, with ct plus 1 plus ct, with ct plus 1 over 1 plus r plus ct equaling this, we can now rearrange that to solve for ct, which is what I'm going to do here. So ct plus 1 equals 1 plus r w minus 1 plus r multiplied by ct. That is just rearranging this equaling w here. We've multiplied by 1 plus r so that we can just get ct plus 1 by itself, and we've taken the ct over the other side. So this is our budget constraint, a lifetime budget constraint that we derived using simple algebra that we just did. And we're now going to draw this on a graph just to make it a bit clearer. So the reason we've written it in this way is to kind of make the slope of our budget constraint, which I'm about to draw, a bit easier to understand. So with ct plus 1 on the y-axis, which is equal to this, and ct plus 1 on the x-axis, we can see here that the slope of our budget constraint, which is going to look like this, is going to be minus 1 plus r. Because the slope of our budget constraint is just going to be how is ct plus 1 changing when ct change. So in other words, the derivative of ct plus 1 of ct, which is differentiating this function with regards to ct, and we're just going to get minus 1 plus the interest rate. So that's the slope of our budget constraint here. So when we change ct, ct plus 1 is going to change by this. And this equation right here makes the intuition behind that a bit easier to understand. So when this changes, this is going to change by this here, because ct is multiplied by this. So I'm also going to derive the intercept points of this budget constraint, so the points here. So looking at this, we do know that it's just a simple linear function. So if we start at ct right here, which equals this, so we know the intercept on the y-axis is going to be when ct equals 0. So if we come all the way here, when ct is equal to 0, we know that this area of our equation is no longer going to exist because we're going to multiply by 0. So we know the intercept is just going to be here, 1 plus r, because that's what's going to be left when this goes to 0. So this is our y-intercept, just 1 plus r. Our x-intercept is just going to be, what is this equation going to equal when ct is equal to 0 with regards, when ct plus 1 is equal to 0, sorry, with regards to ct. So that's just going to equal w. So we have our utility function over the two periods here that we talked about earlier, and we have our budget constraint here. Consumption in the first period plus consumption in the second period discounted by the interest rate equals lifetime wealth. So our consumers want to maximize this function here. They want utility from consumption in period 1 and period 2 to be as high as possible. So they want to consume as much as they can to get utility from that consumption. However, they're limited to how much they consume from this constraint here. So what we need to do now to derive our Euler equation is just some constraint optimization. So we know that we want to maximize this function subject to this constraint here. And we have the slope of both the indifference curve derived from this function, and we have the slope of our budget constraint. And we know that when the slope of these two are equal, we have maximized this subject to this. So here we have the slope of our indifference curve derived from utility, and the slope of our budget constraint derived from our budget constraint. So ignore this graph for a second. When the slope of our indifference curve is equal to the slope of the budget constraint, we have maximized our utility function given the budget constraint. So now looking at our indifference curve, remember the slope of this curve here is equal to this, and the slope of our budget constraint along here is equal to this. So when these two are equal to each other, this corresponds to this point here where the arrow is pointing. This condition corresponds to this point. We cannot consume any more consumption past this point because the constraint won't allow us. We can't consume anything above this area because we're past the constraint, we're past this line, and so the constraint won't allow us. We can consume less than what we earn down here, but we don't want to do that. We want to maximize our consumption given what we earn, given our constraint. So that means we are at this point here maximizing our utility given the budget constraint. So now we know that this condition here is where consumers maximize their utility from consumption given their budget constraint. This is our optimum point. In order to get the Euler equation now, we just have to rearrange this optimum solution and get it in terms of U of Ct. It can be rearranged in many ways. It doesn't really matter. It depends how you want to try and interpret this. But this is our optimum solution. We're just going to rearrange it. See, there's two minuses here, so these will cancel out. So you can take those out. And then we're going to multiply through by our denominator. So we're just going to get this. And this is our Euler equation. This is the necessary condition now for the optimal consumption plan, because along this plan we're maximizing consumption given our constraint. One thing that we can get and interpret from this equation is that at the optimum solution, at this point here, our agent, our consumers, are indifferent between consuming 1 unit of the good, which gets them marginal utility of this, and saving in order to get 1 plus r units in the next period, Ct plus 1. They're indifferent between those two things. That's why they're equal to each other. And I'm going to do another video where I specifically interpret this equation and play around with it just so you can understand it a lot better. But that's our Euler equation and how it is derived from scratch, starting from the assumptions of the model to this equation right here.